tomorrow, and then it's all out.
So, okay. Hi.
How would they also be on the
Yeah. Okay, so welcome. Good morning, everyone. Welcome to lecture 6. So before we jump into the content of today's lecture, I hope everybody was able to submit assignment 2 on time.
I hope.
Some of you are experiencing issues with Blackboard. I guess those people are not here. So was everybody able to submit on Blackboard on time? Okay. Did you face any difficulties with assignment 2?
Yeah, the first one.
The first part is actually just you recognize that you multiply two Gaussian distributions, it will also look like a Gaussian, and if you take the log of it, it looks like the objective of an ridge regression. Therefore, ridge regression solution is also the solution for this one. You don't really have to do anything, do any algebra. Okay. Okay, so I hope everybody is aware that next week we will have an exam in class. The details of which I will try to send during the week, but in terms of the logistics actually. In terms of content, I've already sent across a Google form which had a bunch of topics, right? So those are the topics which were covered in lectures 1 to 5. They will be part of the exam, and also today's lecture, whatever I'm able to cover. Okay. So in terms of content, that's the syllabus. Yeah.
For the crib sheet, can we use both sides of the 8.5 by 11 paper?
Yeah, you can use both sides. The objective of using a crib sheet or a cheat sheet is you actually go through the content before the exam. Otherwise, some people don't go through the content and still take the exam. Very brave of them, but it's good to go through the content. Okay, so the duration of the exam, it's not fully decided. It could be 2 hours, 2.5 hours. I'll let you guys know soon. But ideally, we will not try to have a time constraint. I mean, you should be able to finish the exam way earlier than whatever the time. On average, you should be able to finish it. And so, don't worry about the time issue. Try to focus on understanding the concepts, learning the concepts. Okay. Okay. I'm trying to. So I was going to demonstrate an example, but my Dropbox has not synced yet, so I will demonstrate an example of supervised learning during a few minutes after we start. So let me start with the first section for today's lecture. So any other questions in between? So we covered assignments, we covered the midterm, some details about the midterm. You should get started with your project first reports. Please read through the document there. It suggests coming up with 2 ideas. Okay, one could be ambitious, the other one should be ideally less ambitious, but you should be able to come up with something like that. Yeah.
Sorry, just one more question. So for the project, I think it says somewhere in the syllabus that we would have to look at some kind of paper or research that was already done.
Yeah.
So are we going to be doing that versus actually taking a data set and then doing our own predictions? I think with the project require that we still review something that somebody else has already written and then try to replicate it or...
Yeah, so I think on the syllabus I said in a one sentence statement of the project, I said we will try to reproduce some of the results, some of the experiments or applications people have done in papers. But in the full project detail PDF, I suggest that you could do either. I mean, if you can be ambitious and try to replicate, for example, sentiment analysis of Twitter or something like that. So some research which other people have already done. Replicating is very useful exercise. It's generally not easy. But at the same time, depending on your background, you can pick your own data set and do something interesting with that.
Without having to reference the work of somebody else.
So if you use some sources from other places, then you should just cite it. But it's okay, and you don't have to. Every project doesn't need to have somebody else. Doesn't need to have a precursor. Doesn't need to have a reference. You can create your own data set. You can run a survey and get your own data set and do some analysis if you want. It's a little bit open-ended like that. So it's just so that people who are ambitious can try ambitious projects, but of course you need to dedicate enough amount of time. You can't be ambitious and not spend, just spend an hour. It's not going to work. But if your background is not in statistics or engineering and you're finding some of these topics a little difficult, you can just scale down and take a look at a smaller data set of your interest in the industry that you are experienced with, and work with that. Okay, it's fine. Okay. So in this lecture, we're gonna kind of take a tangent from supervised learning. So supervised learning is all about having x, passing it through a function that you construct. So I'm going to put a hat there, and I'm trying to replicate output variables. And there are some properties that f hat should satisfy. Hopefully that the ERR of f hat is small, right? That's what you decide. Where ERR actually depends on the joint distribution between x and y. You don't have that, and so you kind of proxy that using cross-validation, various different techniques that we discussed last time. Okay. And within the definition of ERR, there's also, for classification we saw the square loss. For regression we saw the square loss, which is y minus f of x for some model f, and here the model f hat itself. Okay. We also saw another loss for classification, which is called the 0-1 loss. It leads to a loss function which is like this, right? So it's summation of I is equal to 1 to n of the log of the probability of or some parameter of g is equal to gi given x is equal to xi. So I guess either I can put theta hat or I can put g hat, one of those things. So once you construct the classifier, the classifier is going to, on your training data itself, is going to make some predictions, right? It will suggest some class. Is that class the same as the probability with which probability that it assigns to the actual realized class or label in the classification setting? You're just trying to maximize the log of that probability. Okay. So it just comes from the 0-1 loss if you actually substitute the 0-1 loss, which is basically for a k-class example, the loss is just represented as zeros on the diagonal and ones everywhere else, right? On the upper triangle and lower triangular parts of the matrix. If you just write this down, you'll actually get an objective like this. Okay. And for both classifications, so this was regression. I mean, you don't have to use square loss. You can use any other loss that you prefer. Okay, I don't know if I've given examples. For example, you can take a regression loss, which is the absolute value of y minus f hat of x. Okay, this is different from the square. Okay, of course, I mean, if you evaluate the absolute value of, let's say, 5, it's 5. And absolute value of minus 5 is 5. But absolute, square of 5 is 5, right? So they're different functions. You can also take, e to the power something, right? You can take e to the power absolute value of y minus f hat of x. This could also be a loss function. It's your choice to define what loss function you care about. And previously we've also made a connection with maximum likelihood estimation. in particular for the for linear iteration, we said residual sum of squares looks like maximizing the likelihood of a Gaussian data model. Gaussian data model just means that if so instead of writing, so a data model means I'm going to assume something about the joint distribution of x and y. So a Gaussian assumption just means I'm going to assume x fixed. Okay, I mean Gaussian assumption is very loose statement. I mean in the sense loose phrase. Here I'm saying that I'm going to assume x fixed. I'm going to say y is equal to beta transpose x for some unknown true beta. I guess I should plus some additive term, additive quantity epsilon, and that epsilon is normally distributed with some, maybe it's zero mean, maybe with some covariance matrix. Okay, so I mean I can just assume it to be, for example, I can assume sigma to be equal to sigma square in the case if it's one dimensional. So if y is a one dimensional output, x is p dimensional, and I can epsilon is going to be one dimensional. In this case, capital sigma is going to equal to sigma square. Okay. For this model, I said residual sum of squares is proportional to the log likelihood of data. Log likelihood of data. Log likelihood of data is a function of the model parameter. In this case, the model is beta, so it's a function of beta. So to just see that, so let's say you have, so what is data here? Data is going to be yi comma xi, right? That is what is the data. I is equal to 1 to n, and for every I we are assuming a data model. So the data model here is that there is no distributional assumption on x. The only distributional assumption is y is a random variable now, because it's basically an offset here, a deterministic offset, and there is a epsilon which is a random variable, and therefore y is a random variable because it's a function of a random variable, right? So p of xy is completely determined by this description that I've written here. Okay, and the likelihood is just going to be for each I guess. Okay, let me write the likelihood itself. It's typically written as probability of data. So data, for example, let me just write the whole thing. yi comma xi. I is from 1 to n, okay, given beta. Okay, I guess, yeah. So this, okay, another implicit assumption which we don't explicitly write it down here is that I'm going to assume every observation is independent, okay, which just means that me observing yi has nothing to do with me observing yj, okay. So I draw yi from this joint distribution, which just means that there may be a fixed xi, and I do xi transpose beta, add some noise, I get a yi. That yi has nothing to do with the next time I generate some yj. Okay, that's what it means to be independent. Independent just means statistics independent. So two random variables are independent if the joint distribution decomposes into their marginal distribution. So p of xy is equal to p of x times p of y, right, for any pair of values that xy take. Okay. So because I assume independence, I'm going to write likelihood to be, so this notation capital pi is like a product, shorthand for product. Okay. Instead of writing a product of n terms, I'm just going to write a shorthand capital pi. I is equal to 1 to n, and the probability that I'm going to see yi, from xi, I guess, given beta. And I said xi is not random at all. So in this model, we just have to write probability of yi given xi and beta. Okay, same thing. And this one, because yi is just xi transpose beta plus an epsilon, which is just normally distributed. This is just this distribution is exactly equal to 1 by square root 2 pi sigma e to the power minus yi minus beta transpose xi square divided by 2 sigma square. This is just the definition of a one-dimensional Gaussian, right? Any confusion at this point?
From the second step to third step.
Like from so this is what we're considering second. So I said in this model xi is not random. So actually to be more precise, I should not write xi on the left hand side of this joint distribution. Okay, it's a given data. You're not assuming any you're not assuming any randomness model on xi. Okay, so this is a bit imprecise. So I should have started with xi always on the right hand side of that perpendicular line. But here, so till second line, I have not really said anything about the model that I'm assuming. So if you start with if you're thinking of maximizing likelihood, okay, up to second line is just a common step. If you have data, you're just asking what is the likelihood of the data. What is the likelihood? First step is saying what is the likelihood of all my data given my model. It could be beta, it could be some arbitrary model, it could be a KNN model or whatever. The second step is saying I'm going to assume independence. So each xi yi has nothing to do with xj yj. Basically, that's why I've written it as a product. I just said the joint distribution of a bunch of random variables breaks down into a product of individual random variables if they are independent. Okay. So till here I'm not really substituted any data model. From here to here I'm saying because our data model assumes x being fixed as non-random. Fixed just means non-random. And I'm assuming y to be just only y to be random because y is a function of a fixed quantity plus a random variable. Okay, so that's why I just wrote it this way. And this conditional distribution, this probability is just this one. Given beta and xi, this is the mean of this random variable yi. Is this clear? So we just substituted the definition of Gaussian here, and this I'm just repeating what we did before. Now you can take log of the likelihood. So ideally we would like to maximize likelihood. Okay, this is the likelihood. I mean, we have completely written down. It's a function of n, it's a function of sigma, it's a function of beta. So we've completely written down everything about the likelihood. You can now just maximize the likelihood over beta. Okay, that is the parameter to get the best parameter. The parameter that maximizes the likelihood of the data. That's what it means. Okay, but this looks a little bit unwieldy because of the product terms. Product of a bunch of exponential terms looks unwieldy. So we can apply a log transformation. And that's because log doesn't change the location where a maximum occurs. Okay, that's a fact. Let's assume that's a fact. So we can, all I'm saying is you can take a log transformation without altering anything in the narrative. So we're going to take a log transformation, and so log likelihood is going to be equal to okay. Actually, in the model, let's assume that sigma is also known. I mean, you don't have to make these assumptions. I'm just making it illustrative example. Okay. Sigma is known in this example model. If you take the log, the product just decomposes. Log of a times b is log of a plus log of b. Okay. The log, let's assume it's base e. Okay. And so the product becomes a sum of I is equal to 1 to n of I'm going to ignore this because sigma I said is known, so this coefficient is something which is a constant. Then I'll get minus yi minus beta transpose xi the whole square divided by some other constant, but let me just say it is constant. Okay. So log likelihood is this. So maximizing the log likelihood over beta. So now I want to maximize, I think I've used an expression for log likelihood once later. Okay, so maximizing this, let me call this L of beta. Maximizing L of beta over beta is basically equivalent. I'm going to use 3 equality signs to this notation. So this is the same as residual sum of squares. Maximizing or beta of residual sum of squares of beta, right? Except for the scaling constant, sorry, not maximizing, minimizing. So maximizing a negative term is the same as minimizing a positive term, okay? That's another fact that I'm gonna, so there's a negative here, right? And I'm, it's negative here and I'm maximizing over betas. Maximizing over the beta parameter is the same as saying minimize over beta of the positive version. So you can get rid of the negative sign and say I'm going to minimize over beta. Okay, and that is just the residual sum of squares, right? RSS is just yi minus beta transpose xi square, right? I guess that's fine, right? So this is a connection that we drew a couple of times in the past. We said even though we choose loss functions, there is a more general way of talking about these things where you think of maximizing likelihood. So you assume a certain data model, some description of the joint distribution between x and y, and then you can define what a likelihood is, and then you can maximize likelihood or the log of it, and just it happens to be, if you make Gaussian assumption, it happens to be the same as minimizing the residual sum of squares. But so the tangent today is going to be that we're going to step away from that supervised learning setting that we saw here. So this setting at the beginning of the, here I've written x goes into some classifier or a regression model, and out comes a quantitative variable y or a qualitative variable g. I'm going to now think of using data in a more general setting. So I'm going to have, I think I used the notation, I'm going to have z as my data. Okay, it's not an input variable or an output variable, it's just a variable. I'm going to enter into some procedure, okay, some statistical. And out comes something, some estimate, okay, it's going to be, let's say, theta hat. So it's an estimate, not it's not an output variable, and with that estimate I can do some downstream task. Okay. So what is the example which kind of grounds this? Let's say I'm estimating the mean of a random variable. Then, okay, for example, my data model here could be that PZ is actually a normally distributed random variable with some unknown mean, and maybe variance is 1. Okay, let's assume that Z is a random variable which is normal with unknown mean mu and variance 1. So the only parameter here which completely describes the distribution on Z is just mu, right, the mean. Now the statistical procedure can be as simple as saying I have observed Z1 to Zn, which are n observations, okay, n realizations of this random variable, and from here I have to have an estimator which will give me an estimate of which hopefully is close to mu. So what is that estimator? It's going to be, for example, as simple as 1 by n somehow I is equal to 1 to n of Ci. Okay, this is my estimator, this is my function of data, so this is going to be my new hat. Okay, I'm using generally theta here, but think of the, it's an estimate of the parameter of the distribution. So new hat is estimate, and hopefully you hope that new hat is close to mu. Okay, right? So that's an estimation problem. That's a statistical problem which doesn't fit into your idea of supervised learning, but it is, this is how it's connected. Okay. And why did I write new hat to be the estimator? If you actually write down now, if you actually follow the follow the MLE procedure, which means that you write down the likelihood, it's going to be a product of bunch of Gaussians, you write down the log of that, and you say I want to maximize that. Okay, it just turns out that maximization over that gives you this answer. Okay. If I have time, I will get back to this in the second part when we're going to do review. But for now, let's assume that that's true. Okay. Okay. Okay, so is the method of maximum likelihood clear? It's just write down. So the starting point is you need to have some hypothesis or some idea of what is the roughly the Jones distribution, how it looks like. Here, Jones distribution or air distribution. Like here, for example, I said some distribution on Z. I'm just assuming it to be normally distributed. Okay, that's the starting point. Once I assume that it's going to be normal, it will have its own parameters, the mean and the variance in this case. And using data, I want to come up with estimators of this mean and variance, which are the parameters of this distribution. Similarly, that's what we were doing even before. Okay, we are estimating the parameters of this distribution, and the parameter just happens to be just beta here. Okay. So before we go into so today's topic, really, core topic is actually trying to understand a more interesting version of maximum likelihood estimation, which is called expectation maximization method. But before we jump into that, I want to cover a topic which you may have seen in statistics, or you may not have seen. It's called the bootstrap. Has anybody heard the word bootstrap before? In data mining, as in 572, it's been covered. Okay, it's been covered, so you guys know what bootstrap is? Okay, how many of you are not doing the data mining course actually? Wait, everybody is doing data mining? That's very surprising. Okay, so the thing is, all these statistical ideas are very simple, straightforward, so just needs to, you just need to have good foundation. So let's see, bootstrap. Okay, let's see. And the reason why I'm introducing bootstrap is, till now we have been just making a prediction, which is a single number. Let's think of just a regression problem. We are just making a prediction which is a single number, right? So y hat, somehow, let's say in linear model it's going to be beta hat transpose x for any given new x. That's a single point estimate. It's called a point estimate. I'm outputting a single number. But sometimes you actually want to know what could be the error in that estimate. Okay. Like you just don't want to report a single number, but you also want to report something called a confidence band. Okay, I'm not going to use confidence interval because you've probably seen confidence interval as a phrase before in some other context. But just think of it this way: I want to quantify the uncertainty in my prediction. Okay, it makes more sense in the regression setting, as in when the output variable is quantitative. So the problem is this. Okay. I just don't want y hat, which could be, for example, for a linear model, which could, for any model, it could be f hat times f hat of x for at a new point x naught. Okay, this will be my prediction. I just don't want this. I also want to understand the uncertainty. By which, one way to understand the uncertainty is to suggest some confidence band. Okay. Which says my output, my prediction is going to be in an interval rather than a point estimate. Okay. This would be a point estimate. I'm just putting a single number. Okay. So one way to address this problem, so for this problem, we want to understand the uncertainty, and one way to address this is to generate a confidence band, which means that I want to say y hat belongs to some interval, okay, interval a to b, okay. Instead of saying at a point x, I have an estimate at a point x naught. I have an estimate y hat. I want to say, okay, this is ranging between two values a and b, okay. And one way to address that is so how do you create these confidence bands? One way to do it is to use the technique of a bootstrap, okay. So I'll just tell you what the procedure is first. And the procedure is as follows. So let's say we have a data set Z. Okay. I want to use. Okay. I'm going to use again some tags at the top and the bottom to suggest that this is actually not the random variable Z, but you can think of this as a matrix Z, for example. So it's Z1 transpose to Zn transpose. Okay. Maybe it's n times p. Okay. Is this notation clear? Actually, okay. Maybe I should use Z. Okay. These are the realizations of the random variable capital Z, n in number, and that's my data. I've just put them as rows in my matrix. These are p-dimensional vectors, realizations, and so this is my data. Okay. And independent of what I'm going to do with this data, okay, this data could be, for example, each little zi could be xi comma yi just concatenated, okay, it could be. But even before I talk about what I'm going to do with this data, I say, okay, let me generate copies of data, copies based on this data, which I'm going to call Z star B. Okay. So of course one of them is not a number, so let's say, sorry, not a symbol, so let's say B is equal to 1 to B. Okay. So I'm going to create copies. Okay. One way to just copy is just copy the data, right? That would be identical data. But the way we're going to generate copies of the data is going to be for, let's fix a B. Okay. So the first copy, let's say, which is Z star 1. So the way to generate Z star 1 is you sample with replacement from Z. Okay. Sample n times. Okay. So I have these this original data, the Z matrix. I'm going to sample the rows of Z matrix, which gives me, like for example, in my first sample, maybe I got, Z1 itself, that I'm going to plug as my first data point in my new copy of data. And then I'm going to again sample again from original data. Maybe by coincidence I got Z1 again. Okay, that's what with replacement means. I'm not going to exclude Z1 the next time I'm going to sample. Okay. And that's how I get the second observation in Z star 1 and so on. So, and I'm going to repeat this sampling n times, okay, and I'm going to fill the rows of this new data set Z star B, Z star 1, okay. So that's just creation of the new data sets, okay. And they're not really new because I'm really reusing the observation that I've already seen, in my original data set. Okay. And that's it. So this is pretty much the crucial and straightforward step in the bootstrap. So these are called bootstrap samples. Okay. Bootstrap replications. then what you do is for each b, little b, 1 to b, okay, do statistical estimation. So this could be, for example, regression, classification. It is okay. Classification. I guess let me not talk about classification because we're talking about intervals around y. So let's think of output being quantitative. Let's say we're doing estimation. What is it called? MLE. Okay. You can do MLE, right? Just like in the previous case, I was in this example. For example, I was saying I'm going to have here, for example, given the n observations, I was creating an estimator of the mean, which is just the average of my observations, right? So I could do the same. I could take this average for every bootstrap sample as well, right? This average, I took the average of the original ZIs, observed ZIs. I could take this average for the bootstrap observations as well, okay, which were sampled with replacement, right? So that is what I mean. Do statistical estimation. You could do MLE as well, okay.
So are you assuming that the distribution again is normal?
No, I just gave an example of a specific MLE problem where we assume the distribution is normal of the data Z. Here we are not making any distribution assumptions. Here we're just saying I have my data which has n observations. I'm going to recreate b copies of it by sampling with replacement from the original one, and that's it. Now I have b copies, and of course the original one. I can always do whatever learning task I do. It could be, it could be regression, linear regression, lasso, ridge regression, something, okay, and I create whatever I want to create. For example, it could be a prediction model, or it could be just the MLE estimation, in which case, given the data, I just estimate the parameter of the joint distribution. The parameter of the joint distribution in that example was just the mean, okay. Yeah.
So the size of each sample that you give is the size of the entire data. So each Z is...
Yeah, each, here for simplicity, I just said sample n times. You could change that, and that will give you variations, but...
So is there a minimum?
No, so these are choices that you need to make. Why should you choose a certain capital V, a number of copies? Why should you choose exactly n, samplings in each copy? These are choices. Okay. So in this version of Bootstrap, I'm gonna set the choice of the number of samples to be exactly n, which is the same size as the original data set, and b is a free parameter. You can choose whatever you want. Okay. Good question. And so if you do statistical estimation, you'll get for example, let's say, so you'll get a f hat, for example, right? If you're doing regression, right? F hat, let me index it 15. F hat star b, okay? Let's say I got these different prediction models, okay? Right? I've changed the data. For each data I'll get a potentially different prediction model, okay? Now, and that's it. So that's a for loop here. You collect all these prediction models, and then you can, and then you are supposed to create confidence bands, right? That was the objective. And that's going to be for any given x naught, okay? That's a new point, or any point x naught. I'm going to just make those predictions, okay? That's going to be my vector of predictions, right? F hat star 1 of x naught, f hat star 2 of x naught, so on to f hat star b of x naught, right? These are my predictions that I can make because I have different models for each copy of my data, right? and my prediction prediction itself can be just the average of this vector. Okay, average of this vector above, and the confidence band can be we call this percentiles. Okay, percentiles are there. So what do I mean by that? So think of, so these are all numbers, right? Different predictions. So remember, y is a quantitative variable. So let's say my predictions are, so example, let's say my predictions are 1.1, 1.3, 1.2, 1.1, 1.09, 1.4. Let's say these are B6 here, whatever, right? I have these predictions. These predictions from the different copies that I generated. Then my prediction itself is just going to be the average, okay, which is just the average of these numbers. I mean, you don't have to take an average, you can take median as well, it doesn't matter. We want to focus on the confidence band part. So what is the confidence band now? It's just going to be percentiles of this vector, okay. Percentiles means just the what is the if you sort the vector, and then take let's say arbitrarily, like second from left and second from right. So you just sort this vector. So if you sort this vector, what happens? You'll get 1.1, 1.09, 1.1, 1.1, 1.2, 1.3, and 1.4, right? I'm just saying take the second from the left, take this as the left hand side of the band, and take this as the right hand side of the band. Okay. These are just percentiles. I mean, you might start seeing percentiles if you in the basic statistics course, but it's just sort your data and take. So if you need a 10th percentile, and if you have 100 data points, you kind of take the 10th data in a sorted vector. Okay. 10th percentile from the left would be just take the 10th entry if you had a 100-dimensional vector. Okay. Here it's not 100-dimensional, so I just set the percentile to be just take the second from the left and second from the right. So you're just excluding things on the edges, on the boundaries of the sorted vector. That's all. Okay. It's the same intuition as like confidence interval that you might have seen for Gaussian distribution, something like that. Okay. So that's it. So this is I would say a heuristic at this point, because I'm only telling you the procedure of how to generate a candidate confidence band, right? It turns out there is some statistical backing to why you should do this, to kind of generate a confidence band for your predictions. Okay. It may not be just for predictions. Instead of f hats, you could have estimates, right? These could be the means, for example, the unknown mu hats in the one-dimensional MLE problem that I was showing here. So in this problem, z was one-dimensional random variable, and I had n copies of it, from which I was generating a mean by just taking the average of these observations, right? So for each copy, maybe I got different mean values because each data copy may have different observations, right? I'm sampling with replacement. So maybe these were the means, 1.1, 1.3, 1.2, 1.1, and so on. Then my confidence band for the new hat would be 1.1 to 1.3. Okay. That's the only variation. So it's not tied to it's not tied to supervised learning. It's not tied to regression only. It can also be used for estimation. Instead of point estimates, you can get a band within which you think the estimate is. Okay. Yeah.
you have different statistical estimators for each B, or is it required to have the same procedure? The ultimate aim if it's the same mass or statistical estimator, then we are having variations and variance and populations.
Yeah.
But if we have different structural models for each B,
Yeah.
then again, it's two ways, but I mean, not very similar.
Yeah, so in this version that I told you, it's the same estimating procedure. For example, you may be doing the same lasso thing on each data set, or the same linear regression on each data set. You could go from, it's a very completely different setting where you could, for one data set you could do k-nearest neighbor, or for one data set you could do linear regression, for one data set you could do something else. That's a different problem. Okay. Here is the same estimator. Same estimation procedure. Okay, whether it's a supervised learning task or the maximum likelihood estimation problem, it's the same procedure. The only thing that's changing is the data set. Okay, you keep the estimation pipeline the same. The only thing that's changing is the data set. Yeah.
But you said we can use different methods for each sample. If we use that, how are we supposed to check the mean or give a percentage like that? Because each method will generate different means. We cannot compare it.
That's true. So I didn't say that is a part of Bootstrap. I said you could use different methods, but that's a completely different problem. Maybe it's closer to something called ensembling. So you have different models and they are predicting different things, and then you just want to have an average number. That's a different problem, I think.
When you take the confidence term, is it a percentage?
Yeah, you just chose. So this is again a choice that I made. Take the second from the left and second from the right. I just made the choice. Typically you want to mimic the way confidence intervals are chosen. So typically, I don't know how much you've seen this, but for example, so I don't know if you've seen confidence intervals for linear regression. I didn't talk about confidence intervals for linear regression, but there they say whatever is your estimate, you do a plus or minus 1.96 times the standard error. I don't know if you know this. It's basically trying to say, whatever is a new hat, there's a new hat here. I'm going to assume that new hat, not assume, but it turns out that new hat has a normal distribution. So see, new hat is a function of your data, right? You just saw new hat, for example, where is that? Yeah, new hat, you see here, is a function of these n data points, right? You can think of these n data points as random variables, and so new hat is also a random variable because it's a sum of a bunch of random variables, right? And so it turns out something called central limit theorem, that doesn't matter. So new hat also has a normal distribution. Okay, if new hat is a normal distribution, you can create a confidence interval of your estimate by saying I'm gonna, whatever new hat I ultimately produce, I'm gonna put a band around it such that I can report that new hat belongs to okay, not new hat belongs to this, but such that so this point is going to be 1.96, minus 1.96 times standard error of my estimate, and plus 1.96 times standard error of my estimate, and the claim here is going to be that probability that the true mu belongs to this band, this interval. So this is completely specifying interval is going to be equal to 1 minus alpha. So here there's going to be alpha by 2 mass, here there's going to be alpha by 2 mass. So alpha by 2 mass just means that the area under this curve of this normal distribution from this point all the way to minus infinity, and from this point all the way to plus infinity. Okay. So I'm saying that the probability mass of the true unknown mu belonging to this interval, which was derived from data, is going to be equal to something like 1 minus alpha, and alpha typically is chosen to be 5%. So 1 minus alpha is chosen to be equal to 95%, and so you kind of chop off. So since I'm assuming a normal distribution, all I'm trying to do is chop off 2.5% on the left and 2.5% probability mass on the right. So I have a 95% probability mass of covering the true nu. Okay, that's where the intuition comes from of what would be the right size of the confidence interval. But here you can just choose, basically you're just trying to chop off some extreme points on the sorted array, some initial bunch of points. For example, I chopped off 1.09, I chopped off 1.4. It's just a choice you can make. Okay.
So imagine instead of taking the percentile,
Yeah.
the distribution is normal standard deviation.
Yeah, that's right. So here we are making an assumption about normal distribution, and therefore we are using standard deviation here. So standard error here is the standard deviation.
So I'm assuming that
Here we did not talk about anything about any distribution assumption. So Bootstrap has nothing to do, is not making any assumption about the distribution. Right? Bootstrap is just saying just make copies of data with replacement, and then you'll get a confidence band. And that's why I'm using the word confidence band rather than confidence interval, because confidence interval in statistics most likely assumes this normal distribution assumption, okay, which we don't need. So therefore Bootstrap can be used for any procedure. So if you're in your assignments or in your project, if you're making a quantitative prediction, you can always do Bootstrap. You can also always apply Bootstrap procedure to get bands around your estimates. Okay, and that is true irrespective of whether you're just doing linear regression or if you're using subset selection and cross validation, a lot of different things to get to your final estimate. Okay, as you can apply Bootstrap very generally. Okay. So there is no normality assumption in Bootstrap in the description I gave you. I think I'm trying to see if I got it. So there's a picture I wanted to show you. So here's a one-dimensional data on the left side, okay, which looks like this. Okay, it's just one-dimensional data. It turns out for this problem, so what do you want to do? So I have gotten this data. Here I have x, which is one-dimensional input variable, y is one-dimensional output variable, and I want to find the f hat which predicts y. Okay, it's a regression problem. One interesting twist in the story is that they want to transform x. X is one-dimensional, but they're going to transform x into 7 numbers instead of one number using what are called basis functions. So basically, if you remember, we could do feature transformation, right? We could, if you remember from regression, if I had input x, I could always create log of x. Maybe I could create x squared, maybe I could create square root of x, and so on. So even if my x is one-dimensional, I just created 3. I created just a 3-dimensional input, which ultimately is used for my regression, right? Which is ultimately used for regression, right? So from one-dimensional input, I created 3 intermediate features, feature coordinates, like taking a log, taking a square, taking a square root. Similarly, think of, in general, again and x, I created functions. I don't know if I used it. Okay, I created some functions. Let's say h1 of x, h2 of x. In this case, they create h7 of x. Okay. They basically, from one-dimensional feature vector, they create a 7-dimensional feature vector. So, okay. So that's the only twist. So think of, although we are seeing a one-dimensional plot of x versus y, it just happens that in the supervised learning problem, they just made the input 7-dimensional. Okay, by just taking functions of x, arbitrary functions of x, and then once you create the 7-dimensional vector. Okay, now just do linear regression in the 7-dimensional space. So you're just computing beta hat 1, beta hat 2 to beta hat 7 by just doing linear regression. Okay, that would be this green curve at the top left of this picture. Okay, so y is not linear. We're doing linear regression. Yes. Yeah, in the transform space it's linear. In this space it's not linear. Okay. Is that really clear why this is not linear, even if you do linear regression? Okay, just a basic check. Now, if you do this if you do confidence intervals, it happens that with linear regression, with appropriate assumptions, beta hats are going to be normal. So each beta hat j is going to be normally distributed. Okay, and so you can talk about confidence intervals for beta hat. Okay, we have not discussed that in this class, but you could use some normality assumption and talk about confidence intervals for beta hat j for each j, or you can also talk about confidence intervals for each prediction. Okay, it's all going to be normally distributed and so on. So some nice properties hold. So anyway, the upshot of doing that is you get a band like this, which is in the dashed line. Okay, this dashed line is from a confidence interval based analysis, which we have not done. Okay, but what we have seen today is more general than that. So it's not specific to linear regression. You can do it for any method, and that basically is for every data set. So create your replicated data sets, these copies z star b. Okay, and then you fit functions. So here the blue curves represent I don't know how many functions they fit, but all these are different functions that they fit. Okay, so basically for each copy of data, you created a linear regression model, and in one dimension, and these are the curves for those linear regression models. Okay, these blue ones on the bottom right, bottom left, and the confidence interval. So the confidence band now is just going to be for every fixed x value, just evaluate these functions and chop off, the outliers on both sides of the sorted vector. You'll get the confidence band. So you see there's a difference in the confidence bands between here and here, but this procedure is more general. Okay, the bootstrap procedure. Okay, so that's an example. Any questions?
Basis function uses the 7-dimensional function.
Yeah, so basis functions are just think of these h1 to h7 as basis functions. Okay. So just to wrap up Bootstrap, there's one other thing that you could do with Bootstrap. Okay. Which is you can estimate ERR. Okay. So remember in the last class we were trying to come with estimates of ERR, and we said we can do AIC or BIC, which would kind of use the little ERR bars, which are basically in-sample errors or residual sum of squares if you care about just linear regression and square laws. And you could do cross-validation, which actually does this k-fold, and it somehow so all these are procedures for estimating ERR. You can also use Bootstrap to estimate ERR, okay, without the notion of validation, and it's just as follows. Okay. So we created these k copies, right? Sorry, these b data copies, right? And we created these f hat star b's. Okay, these are the functions that we got, right? Which would be prediction models, for example. Now, the way we're going to estimate ERR, we're saying, okay, let me take every data point. Let me take data point I. Okay. Okay, and just check, in each of the, b is equal to 1, b is equal to 2, and b is equal to capital B. So, did the data point I appear in the first data set? Okay, that's the question. Maybe it did. In the second data set, maybe it did not appear. Okay, maybe in the third data set it did. Maybe in the fourth one it did. Maybe in the last one it did. So, since data point I was not used in the second data set, you can use you can use the model that you built here, so f hat star b, and you can evaluate that on data point I. So you can evaluate, let's say, if you're doing least squares, you can find this number. Okay, so that's somehow going to give you an idea of, since you did not use the data point, in the bootstrap sample while building that particular model, it's kind of saying that I excluded the data point and therefore I can evaluate my performance on that data point. It should be fine because I did not use that for my model. Okay. Is that clear? So all I'm saying is maybe at some bootstrap samples point I was not included, and so for those bootstrap samples, whatever model you created, since they did not use the point I, you can use a prediction made by those models on point I as a proxy for ERR. I mean, you can do a summation over all data points and so on. That is fine, but this is the idea. But the reason why I did not introduce it last time is this is kind of I feel it's still inferior to cross-validation. Okay. So that is just good to know that Bootstrap can also be used for that. Okay. So let's take a break and resume in 10 minutes. Yeah.
This slide we learned some work however from lecture 1 to lecture 5, right?
Lecture 6.
Lecture 6 as well. Yeah. Okay, so I see that from lecture 3 there are some exam questions at the bottom.
Yeah.
So that's like example of the exam questions.
Yeah.
Will you post another example of exams?
No, I mean those are the example questions. So every lecture, I mean not the initial lectures, but I think 3, 4, 5, and even 6 has some example questions. So those would be the style of questions.
Thank you.
Revise just removes the thing which is not there.
That's basically it. So, and like some of the question style will be what you mentioned.
Yeah.
They will be theory and
I mean, sample questions seem to be more subjective, right? So maybe that's the style.
but we also have any MCQs on there.
No multiple choice. I mean, I'm still working on it, but I'm not thinking of using multiple choice.
So going from the other book is okay, right?
Yeah.
Second, I wanted to ask you that you mentioned that something question that you pulled up regarding cross-validation.
Yeah.
And how is cross-validation better than dividing the data into training and validation?
Yeah.
Isn't cross-validation better?
No, cross-validation is repeating that division again and again, right? Because you have k-folds. So if you just divide...
So there are different types of cross-validation, right? K-fold is one type, but normally cross-validation is just testing your data on a validation set.
Well, actually that was not my definition. I was thinking of k-fold cross-validation, so maybe I should clarify. No, just add k there in the question. So just think of that as a typo.
Can you go to the last page of
Let me just allow this.
Okay. Over here is your input. You should see yourself.
So mine?
Over here are three classes.
So this is like whenever the value is not like let's say B2, the value is not there for I.
Yeah.
So we are basically creating a test and we are testing the data I on that model.
Yeah.
Isn't it bad to include evaluate training and test
First,
together?
we're going to teach it to respond with the cat get.
Why? So what is the last statement? Is it better to include? Or
It would be worse, right?
no, because X was not. So I was not used in the second data set, right?
Yeah, so it is basically a test error for that model.
Yeah. For that model, for the second model that I built,
Yeah.
I is gonna roughly proxy test error. Yeah.
Yeah, and other for it is for the training error for B1 and B3, let's say.
Yeah. For B1 and B3, you will not use I to kind of compute.
So that is a training error.
Yeah.
Then at the end we are evaluating training and test error together.
No, we are not, right? We're only gonna sum over those B's for which I was not in that set.
Yeah, so that's what I'm saying. Like we are summing the training and test error.
No, there is no training error summation here at all. There is no training. So if you built a model in some bootstrap sample B, okay, you are never going to evaluate that model on the data which was used to build that model.
Yeah, of course, yeah.
Yeah, so you're not using training error anyway. That means.
Okay, so I have this I in this B1 model.
Yeah.
So I got the error. Like if I am estimating error.
We are not going to estimate that error at all.
Okay.
We're only going to look at the
which
locations where I was not used and only put that square loss.
Okay, got it. And secondly, we will get the different betas from different models.
Yeah.
So isn't that we need to restrict that beta to get to a abnormally large value so that we can reduce the variance, like as same as the ridge regression?
Restrict the beta. Yeah, you can do ridge regression. This our statements were not specific to linear regression. You could have done anything. Any regression model.
So this is the part before the.
This is an outer loop.
Okay.
So yeah, outer loop.
All right. Thank you so much.
Any regression technique.
Okay. Thank you so much.
Yeah.
Just a bit confused about the assignment thing. Like
Yeah.
last time, last assignment, in assignment 1, I submitted the RMD file and the PDF file.
Yeah.
This time, although the TA said mentioned that the PDF file shouldn't be greater than 10 pages.
Who said? Where did they say that? Yeah.
They emailed us.
Okay.
So they said that you have to submit a .r file and a PDF file, and the PDF file should not be should be less than 10 pages.
Okay.
So when you're making the RMD file, basically it's going to be way more than 10 pages. Like because
No,
it
but the
includes-
RMD file is not evaluated in terms of pages, right? It's just a huge
Yes.
file. Why don't you hide the code snippets which are not critical to your answer?
But
Why do you care about
is there a limit? I mean, for 10 pages, is there a specific reason?
It's just to contain his workload, I think. Nothing else.
because like the code runs like the code is already of like 100 lines if you
Okay. Yeah, but there is irrelevant lines, right? I mean, there's going to be common stuff which is not very specific to the answer.
True, but like in the Boston data set which was there in the assignment, so there was this question which was which was saying show some plots related to each individual predictor.
Sure.
So each individual predictor had like 3 plots,
Yeah.
and there were like 7 or 8 predictors. So there were already like 24 plots, and when you plot when you turn it into when you knit it into PDF.
Okay.
Yeah, it was like, so that solution, that only specific solution was somewhere around like 35 to 36 pages.
Okay.
So just getting confused on this.
I think we mentioned in the assignment, try to be concise.
Yes.
So
Concise
try
in
to
a
be
way.
concise. That's I don't know what to say.
Even if we try to be concise, there is a thing like if there is something mentioned very specifically in the question, we have to show it. Like
Yeah, definitely.
showing
of course.
like plotting the graphs with all the predictors. So
Okay.
that is something which is mandatory.
Yeah.
So when you do these things, I asked this on Slack, but I guess
He didn't reply?
No, I mentioned very specifically if it's not.
Then submit your current version and we'll see. I mean, there's not an issue with the.
So I talked to the TA yesterday. He said you can put an appendix below, so you can put all the charts out there. Just write a one-liner what you get out of the question. The rest you can put in the appendix. That's what he told me. And I read
Like a supplement. So at least the main document should not be cluttered. Have to have a concise first document, and maybe you can have different things on the second document.
Okay.
You can do that.
Okay.
I think the page is just to enforce some conciseness for in solutions. Otherwise, people can write 200 pages and it's not going to be feasible for people to TS to grade it.
Yeah.
That's all.
Okay.
So
I have a question to
Yeah.
In the first assignment, it was asked about the flexibility part, right? Complexity, flexibility, etc.
Yeah.
So what I'd answered is, one is increasing degrees of freedom, that is x square in polynomial function of x. And secondly, if I, let's say, have n variables, mx variables,
Yeah.
if I take all n,
Yeah.
then my model will be more complex compared to if I just take 2 x variables.
That's true.
So, yeah, but I have been deducted 1 mark, and he said that the first case does not classify as a complex model. And I kind of argue, but
first case is what?
sorry, the second case in which I am taking all the m dimensions.
Yeah.
He's saying that m dimensions you don't classify it as a complex model. And I discussed it with him, and he said it's. I said I have read it from the book, but
Just
he
send
didn't
an email to
realize-
him with me CC and say this is
Yeah.
what Professor told.
Okay, thank you.
Professor, regarding the final exams,
Yeah.
I sent you an email, but I didn't get it.
Yeah. So actually, let me.
The thing
write it
is,
down.
the tickets which you are going to book, the prices are increasing, so that's all.
For commencement. No, the final exam is on 16th.
Yeah,
The conflict was 16th.
yeah,
and,
16th.
commencement versus the exam, right?
But then the thing is, he has booked the tickets on 16.
That's his unique problem.
Yeah.
That's a bad problem to have. You don't want to have that problem.
Okay, and in my case, I just had a commencement problem.
Yeah, so the commencement, the thing is the department coordinators has not responded yet.
Okay.
So I will follow up.
Okay. Thank you. Yeah, that is all.
Yeah.
I just had a small doubt about when suppose we have a sample where we have 100 data points, so it's a 10 cross 10 matrix suppose, so we can create 10 or 15 whatever sub data sets from that. Okay. That is stuff. I mean we are creating B data set.
You're talking about Bootstrap?
Yeah, Bootstrap.
Okay.
And the size of each bootstrap that we are creating need not be equal. We can have a 10.
You can change it, but here in this narrative, I've said keep them the same.
Yeah, but there's not very hard and fast rule that we should.
If you change it, I don't know what properties like. Thing is, this is
we are. I mean, after we are using the average of the value.
Sure.
So should it matter the size of?
This is not about intuition. You can actually prove that Bootstrap does something nice, which we are not doing it here. Here we are just describing the procedure. If you change n the size of the bootstrap sample and the number of bootstraps, how does it influence the output? You can do it quantitatively as making different assumptions. You can actually give very formal claims of what bootstrap does. We're not doing it here.
And when we are taking data from the main sample from those 100 data points, we are replacing data.
Yeah.
How are we replacing that data? I mean, suppose
replacing it, you have the issue of resampling the same data. That's all I mean by sampling with replacement. Replacement just means first time I sample, I get the first observation. Second time I sample, I may get the same first observation. That's because the first time I sample, I got the observation. I'm not deleting it from my original data.
Okay.
Otherwise, it will be called sampling without replacement. So there's just a variation in sampling. That's all.
First, suppose if we take B1 data set, suppose we took from 10 to maybe 10 to 20. Suppose we
it has to sample, but let's say
it's 10 to 20. We are then, or otherwise we take it randomly any 10 points.
It has to be random, by the way.
Yeah,
in my narrative.
But just for example, we took it 10 to 20 in one.
Yeah.
And so main data will be having only 90 points. So we need to.
No, main data will always have 100.
Okay.
You just sample 10 to 20 in your first bootstrap sample.
Then we'll solve.
We'll do data fitting in on the 10 to 20. Then again you sample. Maybe you'll get 10 to 20. Maybe you'll get 20 to 30. Again any other.
Okay. Yeah. And okay, suppose all the bootstrapping will be done in this manner.
Yeah.
And then we'll take the average.
Yeah. You have questions?
Do you have time or I'll ask after?
Yeah, we want to resume the class. Yeah. We'll resume the class. Okay. So we actually have a choice to make whether to review the midterm syllabus or to go ahead with the topic. Midterm. So I actually sent out a poll, and it seemed like just slide down. The most. I guess the one which had the most interest in terms of reviewing was linear discriminant analysis, model selection, and Ridge and Lasso being the second second place in terms of interest in reviewing. Is that accurate? I mean, you guys want me to review linear discriminant analysis, model selection, Ridge regression, and Lasso. Is it fine?
How about like a general review, like the first points
of every topic?
Yeah, like general themes. I don't know. Like general intuitions, general.
Yeah. Yeah.
Then the topics you weren't able to cover today, will they still be on the midterm?
That's the question. Do you want to be ambitious and you want to do that? Or?
We can save it for next time.
Okay, let's start with actually an example. Yeah, actually, let's see what's happening here. Yeah.
Do you have a bracket chain or something like that?
I mean, you just concatenate the sample exam questions and that's your practice exam. Pattern of what? It's going to be very similar to the sample exam questions. So it's going to be like, for example, you saw some subjective questions, right? So you will have something like that to answer. So most of the questions will be like that. If you care about pattern, you will have some number of questions appropriately for the the duration. I mean, way less than the duration time, hopefully. But the questions will be very similar to the sample questions given at the end of each lecture. Okay. Like that's you'll have like a sequence of, let's say, 10 questions which are all like the same thing, and you just wanna give a 3-line answer or a 5-line answer at most. Okay, let's do. I can't fit all the list in the same. Okay, actually, let's look at a cool example because I think it kind of. How many of you have already tried this link? This link is on the lecture 6 first paragraph, I think, somewhere. Yeah, it's example 1. It's a visual example of how interesting supervised learning can be. So it was made by a few companies, I think Stodge, Useall5, and Google. And it's basically supervised learning. What do I say here? Yeah, so basically here the model happens to be a neural network model, but you can think of neural network model. You can just replace it with LDA or logistic regression, and those are the other candidate models. The candidate models that we have seen are LDA and logistic regression, but here they're using neural networks for classification. Okay, and the classes are 3 classes: green, purple, and orange. And here we are going to actually generate the 3 classes. So okay, let's see how to generate. So here, I think. So actually, I think probably I have to shake the hand. Right? So it's creating examples. So you see it's saying 8 examples or whatever is the number of examples. Okay, I hope my computer doesn't crash. You can also try it on your machine if you want to. The link is on the lecture note. Okay, some number of examples. I don't know if it'll work, but okay, I have 25 examples of my hand open, and it's doing some computation. So the way they're doing it is, once they know the label, they're just mapping it to a.
Try recording some more.
They're just mapping it to a output task. In this case, they're going to just display 3 GIFs. Okay. So green happens to be this particular thing. So let's say for purple, let me just use. Oops, doesn't work. At least 30. Okay.
Okay, you should now see the green bar and the cat GIF.
Okay.
But if you move around like this,
so I'm just creating training data here for each of the 3 classes.
That's because the machine is looking at your input and picking which class it looks most similar to. But since you've only trained the green class, it always picks that one.
Trying to say something.
That's why you need to teach it a second class.
Okay. So these are just variations of the picture, so that it has different pictures. I guess. Okay, I'm just trying to reach 30 here. Okay. Intrusion. Okay, that's the second example, and third example. Let me just use a pen or something. So all we're doing is 30 examples per class, so total maybe 90ish observations. It happens here that these are actually images. You can always vectorize images and think of them as input variables, which are vectors. It may be suboptimal to do so, but you can think of it that way. Okay. So here it just happens the inputs are two-dimensional images, so you can do something specific. Okay. So once you've trained, okay, so now I think it should just directly, yeah, so I think here it's showing some confidence level for each prediction. So for this one, it's saying confidence is 96%, so therefore it's showing this GIF. So if I change it to this, my machine is too slow, but it just mapped to something else. And if I bring in a pen, hopefully the third one is higher. So you can do this. So it's actually in the browser, you're actually training a neural network model. Happens to be a different classifier, family of classifiers, but you can see how quickly you could go from a certain type of input data. In this case, webcam is actually functioning as a measurement device and can generate your full training data set, right? Some training is actually happening in browser on the client side actually, and you map the labels to a downstream task. So it's a nice illustration of supervised learning. Okay. Any questions? Yeah.
So this is actually related to the lecture. So if we're going to go to the midterm instead of the lecture, does that mean the rest of the lecture will still be on the midterm, or?
Yeah. So that's a good question. So let me close this. So we'll have Bootstrap and maximum likelihood estimation in the exam. Okay. We'll not have EM and sampling in the exam. Okay. So someone suggested that I should go through all the topics here, but it's not possible given we only have about 70 minutes, I guess. So I know that from the poll, some of you suggested let's go through model selection, linear discriminant analysis, lasso, and ridge regression. So what style of review would you like? Actually, depends on. I've not prepared any new material, so we're going to use the same material. Okay, because new material means more stuff to study. So let's avoid that. So would you like to go through the whole sequence very, very quickly, or do you want to look at these 4 topics that I just mentioned a little bit more deeply? There are the 2 choices. So the exam questions, for example, there are some example questions here, right? Okay, this one probably is not relevant. 2 and 3 are not relevant. For example, number 1 is quite straightforward, right? So what are the different ways to use Bootstrap in a statistical modeling task? I just showed you 2 ways. One is to come up with confidence bands. The other one is to estimate capital ERR, or the generalization error, right? Pretty much that's the answer here. Yeah, similarly, I think the other questions so for example, the last question is how do you find the final model using cross-validation? So you need to completely understand and not do a misstep in how cross-validation is used. Okay. And the second part of this question is just saying what data will be used to find it. After you do cross-validation and you have figured out your optimal choice, for example, for subset selection, you've already chosen, let's say, a subset of size 3 to be the best subset according to your, or after doing cross-validation, what you get is one estimate of your EPE or the generalization error, an estimate of EPE or generalization error. For every choice, you get one number, for every choice of subset size k. So once you get these numbers, you can see which number is the lowest, and that would be your subset choice, right? Some K star, which will have the lowest estimate of EPE or the estimate of ERR. That would be your choice. But once you fix that choice, you can actually use the full data set, forget cross-validation, and then build a final model with that choice of subset. Okay. So the second part of the question is asking what data will be used. I'll use the full training data. Okay. I will not think of cross-validation at this point, because you've already chosen you've already made the choice of what is the subset size using cross-validation. And once you made the choice already, then you can ignore validation stuff. Just use that choice, build a linear regression model, and that would be a final model. Okay, so that's what this question is expecting. First part, you just need to repeat what cross-validation is, right? How do you find the final model using cross-validation? So let's say you have 10 choices. For each choice, you would do 5-fold cross-validation. So for each choice, you would hold out one fold, train a model on the other folds, evaluate it on the held out fold, repeat it for every fold in turn, average, and that's one number that you get for one choice. And each of the 10 choices you do the same, get the 10 numbers, and find the number which is the lowest, right? And that would be your best choice. So a description like that is needed, and it has to be concise, of course. You can't write history there. Yeah.
Do we have do we have to worry like a calculation question, just like homework and stuff?
No, homework. So the thing is, some people found it odd or interesting that in the homeworks, mostly the emphasis is on computation using R, and the classes it's more understanding, and the language of understanding happens to be some mathematical symbols, where it's on the way to understanding, right? I mean, ultimate goal is understanding. So in the exam, we will not ask you R-related questions or computation-related questions. It's going to be this style. At least for the midterm, it will going to be this type. We may change it for the final. Yeah. Okay. So, for example, what are the similarities and differences between LDA and logistic regression? We've actually written that it's there in the notes above. LDA makes more assumptions. Okay, it makes assumption that the class conditional probability distribution. Okay, I should not use hands. Maybe I should probably write it down. So, like if you do LDA versus logistic regression, one answer could be that LDA assumes probability of x equal to x given G is equal to some class K is normally distributed with some mean mu K and at common variance sigma. Okay, whereas in logistic regression there is no such assumption made. Second thing would be that model needs optimization. In a sense, there is no closed form expression for the logistic regression parameters. You know, beta hat, I guess L's. You know, L is equal to 1 to K minus 1. There are those parameters, right? So those parameters you don't have a closed form expression. For LDA, you actually have. Okay, so that there's a computation. So basically, there's a computational difference and there's a modeling difference. The modeling difference is that LDA is assuming more, and if it happens that what LDA assumes is actually true, then LDA is going to do better than logistic regression. And when I say better, it just means that for the same amount of data set, logistic regression will probably have a worse performance because it's assuming less than LDA. Okay, but anyway, these are the two points, and this is actually written in the notes as well. But so this was just to answer somebody's question about looking at some sample questions, but let's get back on track. So should I look at all the topics in sequence very quickly, or which will be a recap of the whole narrative that we've gone through the past 6 lectures, or do you want me to pick up a couple of topics that you completely, which are pretty tough, and we can revisit them? No, because there's only 1 hour. You want to be, you can't do both, right? Huh?
Last option.
Okay, so how many of you want me to, so in terms of the survey, so I sent out a survey, right? That was to kind of get an idea of which topics people found relatively more difficult, and the survey, the topics which had the highest 5 ratings pretty much, like everybody gave very high ratings, was, high ratings in terms of difficulty or, requests for review, were linear discriminant analysis, model selection, lasso and ridge regression. Those are the 4 topics I can kind of revisit again in the next 1 hour, or we can go through each lecture note, but in a fairly fast pace. Okay. So who's in favor of just looking at the 4 topics? Okay. Who's interested in all the topics? Okay. I think the second set has a higher vote. So let's look at all the topics. So it's going to be a revision for me as well. I have not seen it. Okay. So in lecture 1, I started with a sports analytics application, but let's look at what's happening in terms of the linear model and in terms of the KNN model. Okay. So in lecture 1 we introduced linear model without the notion of statistical language. So basically we said, okay, we're gonna just make a mapping from X to Y, which happens to be X transpose beta, and we're gonna find such a beta by finding, I guess, I don't know, at that point did I call it residual sum of squares, but by just defining residual sum of squares for a model beta to be equal to sum over yi minus xi transpose beta. Square. Okay. And this we just wrote it to be equal to and whatever model happens to be the one which minimizes residual sum of squares has a closed form expression. By closed form expression, all I mean is it can be written as a function of your data set xi yi. Okay. It happens to be X matrix transpose X matrix inverse X matrix transpose Y vector, where yi's are concatenated. Okay. In this case, and it happens that this formula holds even when y is output variable is k dimensional. Okay. So, but let's just stick with 1 dimension. So let's say y is 1. So this is n cross 1, and this is going to be p cross p. Okay. And X transpose is going to be p cross n. Okay. This is the dimensionality of individual blocks in this expression. So we just looked at a two-dimensional data set, and now I don't know whether they're oranges or not. Let's see. The key aspect here in this plot with oranges and blues is this notion of a decision boundary. Okay. And actually in this example we somehow converted, so in this case there was oranges here and blues here. Okay. Maybe these O's here. We actually mapped the G values to Y values. We said, okay, let's pick oranges to be orange to be 0 and blue to be 1. Okay, so we got a quantitative variable there, and we got a decision boundary here. So here the decision boundary was just places where y hat was equal to 0.5. Okay, so wherever you are, so a linear model is gonna create a plane. Okay, think of this, these are two-dimensional data points. X is two-dimensional here, so my prediction is going to be a function of my points, right? For every point I need to make a prediction, right? It's just going to be a two-dimensional plane. Okay, think of a plane which is rising on top of the screen. It's going in some direction, and think of that plane contains lines. Planes contain lines. Think of a line which is exactly equal to 0.5 on that plane. Okay, right? So think of what is y hat. Y hat is just x transpose beta hat for some beta hat that you built. In this case, that whatever beta hat that is equal to 0.5. This is the equation of a line. Okay, this is x1 beta 1 plus x2 beta 2 is equal to 0.5. So it's just a line on this plane, and that when the line is equal to 0.5 is this line. Okay, maybe when the line is equal to 0.6, it's that line, and maybe it's like this. So there's a plane. Okay, and just pick the line which is 0.5. That's the decision boundary. Okay. And we said, okay, and for this data set, it didn't appear as if the oranges and blues were well separated from the decision boundary. So yeah, I mean, it happened that some oranges were here and some blues were here, and you still had like you're misclassifying essentially. Okay, and so therefore we suggested, okay, let's look at a different technique, which is the nearest neighbor technique. And the formula was, it's not really learning anything, so there is no explicit beta hat equivalent here. It's just you're just gonna pick k, and it'll have xi, yi as your data set. And for any new point x naught on that plane, for example, wherever that is, just find a neighborhood of k guys, k points which in your data which are closest to this x naught. Just look at their labels, whether maybe there were oranges here, maybe there's a blue here, it's orange here, and maybe there's a blue here. Just take the one with the, just look at all these blues and oranges which are in the neighborhood, k closest guys, and predict that label which has the highest votes, right? So orange has 4 and blue has 2, then that's your prediction. Okay, that's what KNN does. And then again, even for KNN, you could draw a decision boundary, and that was just happened to be highly nonlinear. Okay, orange is here, blue is here. Okay, and we discussed about what happens for different choices of k. For k is equal to 1, you'll exactly pretty much you'll not probably have two different regions. You may have a total mess which is like this. Let me just show that. So this was for some k, I think 15. K is equal to 15 here for the same data set, and for k is equal to 1, every data point has to be correctly classified, right? For k is equal to 1, the nearest neighbor to any training point is itself, right? It's a distance 0 from it. So if you choose k to be 1, in its own near area, it's going to be the label is going to be the same as the label for the training data. So that's why it's blue here, and in fact, in a little bit of a surrounding region, it's also going to be classified as blue. And so this is your messy decision boundary. So it's not really a single decision boundary. It's like a lot of islands. It's a union of a lot of different regions. Okay. And so that's the effect of choosing k to be really small versus really large. Okay. And the same in the same lecture, we just had an initial idea of what does it mean to choose k, and we said, let's imagine we had a separate test data set, okay, separate xi, yi generated using some distribution assumption that I made when I generated these oranges and blues, which they didn't reveal at the beginning of time, because it's simulated data. They knew how they were generating the oranges and blues, so they created new xi, yi's, which they did not use for the KNN method or the linear regression model, okay. And they said, okay, depending on the choice of k, here it's inverse of k, so think of k being small to be on this side and k being large on this side, okay. When k is really small, you're actually, so the blue curve represents a training error, so you'll make pretty much zero error, okay. That's here, okay. And whereas on the test data you will be making lots of errors. So this on the left corresponds to those multiple regions that you saw in the previous plot, and pretty much towards the right corresponds to a very smooth decision boundary, okay, pretty much a single decision boundary, okay. And there is some sweet spot in between where you have test error low. That should ideally be the k you should have chosen, but you don't know that, and that's why we do cross validation later on, okay. So that's it. First lecture was just introducing the two methods. Okay. So any questions about the first lecture, because it's just it doesn't have statistical modeling language. Yeah. It's not, right? I mean, so when k is large, let's say here it's 1 by k, so think of k large being here. Training error is high. When k is large, you are actually underfitting your data. So when k is large, it's kind of saying the prediction that I make at any given point is gonna pretty much take the average of the whole data set, right? Think of the extreme case where a prediction I'm going to make is just the proportion of oranges and the proportion of blues that I have in my data set. It's going to be a constant prediction. Let's say I have 60 orange points and 40 blue points in my data set, and my k happens to be 100, which means that at any given point I'm going to just take the pole of my data, which happens to be always the same, 60 orange and 40 blue. So I'm also always going to predict orange, okay? And so you're basically thinking of your prediction happens to be like a constant function. It doesn't change depending on the locality, depending on the query test, query point. So is that clear? Okay. Yeah.
So for lower k, I understand we have specified small regions surrounding the line. So is there a point where in between there is curvy linear kind of decision boundary?
Yeah.
But is it the extreme end, the higher k is just a straight line always, or it need not be a straight line?
The extreme end, when k is equal to the whole data set, right? You're asking. So decision boundary will not be even visualized. It will be outside of this data. In a sense, the whole data set is being now classified as one color, either orange or blue. So you'll not even see a decision boundary partitioning any area. It will be outside. Okay. Yeah. So basically, a decision boundary would be where is the thing? So let's say k is equal to n. Let's say this is my data set in this area. My decision boundary will be like this. Okay. Like everything inside, I'm gonna just call it one color. Okay. In fact, not even everything inside. Anywhere, I'll just call it one color. Okay. So this is not even. It's not like on this side I'm gonna call it a different color. It's just the boundaries are at infinity on each side.
Okay. So there need not be any point where it becomes straight.
Yeah, it need not be straight at any given k. It need not be a linear decision boundary. Yeah. Any other question? Okay, let's look at lecture 2. in lecture 2. Now we introduce the notion of statistical models. And so in lecture 2, the most important thing you need to understand is probability of x comma y, which is probability that x takes a value x and y takes a value y. Basically this is a shorthand for all x and y. So basically this object you need to be comfortable with, the joint distribution between x and y. Okay. Some of you are comfortable with it, some of you might not have seen joint distributions and stuff before, but this is a very central object in all sorts of reasoning. Okay. There is this notion of expected squared prediction error, EPE, of a model. Okay. And there is a description which kind of says, okay, I can break down the EPE into an expectation of another expectation. Okay. You can just look at that. It's just algebra. So okay, let me just write it down. So it's expectation over x and expectation over y given x of y minus f of x square. Okay, something like this. And this breakage, the two expectations happens because of a very simple property, which is the probability of x is equal to x and y is equal to y is just the probability of y is equal to y given x is equal to x times probability of x is equal to x. Okay, this is just the rules of probability. Any joint distribution can be broken down, can be factorized into a bunch of products of distributions. Okay, and you can do it the other way as well. You can write the joint distribution is equal to probability of x is equal to x given y is equal to y times the probability of y is equal to y. Maybe that is interesting, maybe this factorization is interesting, depends on, it's your choice. Okay. This breakage happens because of this rule. So you can just expand the definition of EPE and just use this rule, and you'll get this expression. But the central idea in that section is that if you know the joint distribution, okay, this is the first ingredient, and if you knew the loss function happens to be in this case y minus f of x square, the squared loss, then the best prediction function. So we are in the regression case. Okay, the best in terms of this loss. I just defined the loss to be squared loss. Okay, for this joint distribution, for this as in any joint distribution, for the squared loss, the best prediction model, best in terms of which minimizes the EPE. Okay, actually I should write not this, which minimizes the EPE. Okay, is given by f of x for any value x. Okay, let me just write a little x. For any x is equal to the expectation of y given x of y given x is equal to x. Okay. Now it looks like I'm using lots of short forms, so let me actually expand it to make it clear what do I mean here. Okay, so this is just think of expectation as some sort of expectation is just a summation, right? So it's summation over y of the probability of y is equal to y given x is equal to x times y. Okay, this is what this is. This is by definition. Okay, this expectation is this, and this is nothing but probability of y is equal to y comma x is equal to x divided by summation over y of probability of y is equal to y comma x is equal to x. So here I did not really do anything. I just wrote that this conditional distribution can be written. So if you know the joint distribution, okay, that's what I said. The first ingredient is for some joint distribution. Okay, for some joint distribution for the EPE, I told you this is the best model, and this best model is nothing but summing over y of some conditional distribution, and that conditional distribution is actually, you can get it from the ingredient 1, which is that conditional distribution is nothing but the joint distribution divided by sum over y of that joint distribution. Okay, so if you know the joint distribution, you pretty much wrote down the best model or the best prediction you could do in terms of EPE. Okay, see, this is the joint distribution, this is the joint distribution. If you know joint distribution, you can tell me what the best prediction is for the square loss. That's the statement here. Any question? That's the kind of key output of this section, statistical decision theory. Okay. It's saying, let's ignore data. If I had a joint distribution, I'll tell you exactly what prediction I should make. That's the statement. But we don't have joint distribution, and so we do a lot of other things later on in the course. Yeah. Whenever I write capital Y, it's a random variable. So here, f of x is our prediction. Little x is the feature that is given to us at any point. For example, x naught. Let's say I can put x naught. Some point this is given to us. My prediction is going to depend on just the joint distribution, which is like this, right? This whole expression is saying, since I know the joint distribution, I can write the numerator, I can write the denominator, sum the denominator, I can do the summation over y's, I'll get my prediction. This one, yeah. This is just a definition of the expectation. Expectation of something, whatever is on the left side of this perpendicular argument, is just that values that it takes for every given y times the probability of that thing. It's a conditional probability here. That's why. So whenever I subscript something, it's the expectation with respect to that random variable, and here it's a conditional random variable. So this is just definition here. So I guess the first line is just a shorthand notation. So if you're getting confused with that, just think of it this way. Then the best predictor is just f of x naught should be equal to sum over y. P of y is equal to little y of x is equal to x naught. Let's say. Yeah. Times little y. So if you're getting confused with this expression, just think of it this way. Okay. And a similar claim can be made for classification as well. In classification, EP doesn't make sense, so we think of 0-1 loss, or you can have arbitrary loss function. So you think of the 0-1 loss. It turns out that I did not write this here. Okay, I did not discuss that there, so let me just scratch that. Okay, so the first section is saying if you knew the joint distribution, this is the best predictor you can do. Now let's think of what KNN and linear regression is doing. So KNN is actually saying take the average of my k nearest neighbors, okay, in my training data. So my claim is that whatever KNN is doing, let's say f hat of x naught, is f hat of any given point x naught is just find the k nearest xi's in my training data, look at their labels, and then take the average if it's a regression problem, right? And if it's not a regression problem, just take the highest voted label. Okay. So KNN is actually just approximating this expectation of y given x of y given x is equal to x naught. Okay. Right? Because it's just taking. So at a given x naught, you want to find the expected value of y. Okay, given that x is equal to x naught. That's what KNN is doing. It's saying at an x naught, I want to take an average of y's, but at the x naught, I haven't seen any y's in my training data. Let's say I'm just taking the average of y's for k's for x's which are close to me. Okay, that's the intuition. Ideally, you're supposed to take an average of y at x is equal to x naught. I'm saying KNN does the average of y's for points which are close to that x naught. That's why it's approximating this conditional distribution. Okay, and linear model is saying linear model is saying I'm going to approximate my, this is the best model that you could come up with. I'm going to assume that the best model is actually linear. I'm going to make a linear assumption on the best model. Okay, that's what it's doing. So it's not a local assumption it's making. It's saying that I know that f of x naught for any given x naught is supposed to be this, but I'm just going to assume that this conditional expectation is actually linear in x. Okay, that's a very strong assumption to make, right? But this is what it's assuming. That's the interpretation of bringing in this statistical addition theory. Okay.
So, this question of linear assumption. For KNN, it makes sense you're averaging out and
Yeah.
your expectation.
Yeah.
But for linear, it doesn't make sense. Why is it?
It's an exogenous. It's like you're making a strong assumption that this conditional expectation is linear with respect to x naught. It's a strong assumption. It may not hold. Yeah. It's just an assumption to work with. Yeah. It's not doing any averaging. It's not trying to approximate this. In a sense, it's actually imposing that it has to be linear. Okay. It's like, yeah. But KNN is saying, okay, I have an expectation which is supposed to average over y's. I am doing something sane in terms of averaging of y's of close enough points. Okay, at least KNN seems sane here. Linear is making a lot of assumptions, but the advantage of linear is that linear is going to work in high dimensions, and that brings to the next point, which is the curse of dimensionality. Okay. I mean, so at this point it looks like KNN is the winner, right? I mean, it's doing the right thing. But because of curse of dimensionality, you can't use KNN all the time. Therefore, we need those other methods like ridge regression, lasso, just linear regression, all these other guys, okay? Or LDA or lossy regression, all these guys. So curse of dimensionality is just saying that so there are different manifestations of curse of dimensionality. Okay, I skipped the ET counterpart for classification, but it's very similar interpretation. Okay, I don't want to repeat it. So one of the manifestations of curse of dimensionality is this I can't remember this. So this idea that when you want a constant fraction volume, let's say I want to cover 10% of the volume of my input space. So let's say each coordinate of my input variable is a number between 0 to 1. It can only take a number between 0 to 1. So each coordinate of my input variable can only take a value between 0 to 1. Okay, that means that I have a 0 to 1 cross 0 to 1, for example, in 2 dimensions. In 3 dimensions, it's going to be cube, which is 0 to 1 cross 0 to 1 cross 0 to 1, right? So for the same, let's say in some dimension, so let's say in 1 dimension, what is the fraction, so what is the edge size to have a 10% volume of the total input volume? Okay, so it's just asking what should be the size of the neighborhood that you need to choose to capture 10% of the volume of your input. Okay, let me just do that pictorially, it's kind of easy. So in 1 dimension, I said, let's say in 1 dimension my input is only going to vary between 0 to 1, and if I want to capture 10% of this volume, in 1 dimensional case the volume is just going to be length. Okay, if I want to capture 10%, I just have to take between 0 to 0.1 or whatever, wherever I want to capture 10%, it's going to be the length is going to be 0.1. Okay, this length. Okay, in 2 dimensions, to capture 10% of the volume, okay, I need how much side length? So I need x square is equal to 0.1. Okay, this is the side length that I need. Okay. Similarly, you'll see that in p dimensions, you need x is equal to 0.1 to the power 1 by p. Okay, and it just happens that this number gets closer and closer to 1 as you increase dimensions. So what does this mean? This number is trying to represent the side length of the neighborhood that you're trying to capture 10% volume. Okay, 10% is fixed always. To capture 10% volume, the side length that I need in high dimensions is almost as if I need the whole side length. So the side length max value was 0 to 1, and it happens that x is almost close to 1, and that's depicted in this picture. Where is this? So think of the 10% as this line. Okay, this where I put the cursor there. Start going up. So for one dimension, this is 0.1. Okay, the side length is 0.1. For 2 dimensions, the side length is actually 0.2, 0.3. Okay. For 3 dimensions, it's 0.45 or something, and for 10 dimensions, it's already 0.8. So you need to have side lengths which are 0.8 on each side of your 10 dimensions to have just 10% of the volume. Okay. So where is the rest of the volume going? It's mind blowing, right? You're taking 10%. You're taking 80% side length on each dimension, and still you're only covering 10% of the volume. Okay. It's crazy. Like so I'm only leaving 10% on each side length, but that's still capturing 90% of the remaining volume. Okay. That's the this dimensionality issue, that even if you're considering full ranges, you're only capturing 10% of the volume. And why is this interesting for KNN? Because KNN is a method which thinks of neighborhood points. So in high dimensions, to capture, let's say points are uniformly distributed in high dimensions, then that means that if I capture 10% of the volume, I will roughly have 10% of my data. Okay, that's what that means. To just have 10% of my data as neighbors, on each axis I am looking at a side length or the neighborhood length between almost in this case 0.8 of the whole range. Okay, it's as if the neighborhood size is like really huge, right? In each coordinate I'm saying if my current let's say x0 is 0.5, 0.5, 0.5, 0.5 in p, even in all the 10 dimensions, then I'm saying take the neighbors which are 0.5 plus or minus 0.4. Okay, the neighborhood size is like really huge, just to capture 10% of the points so that I can make a prediction. Okay, so if I have 100 data points and I need 10 neighbors to make a prediction, okay, let's say k is 10. Okay, I need 10 neighbors to make a prediction. To get those 10 neighbors, I need to really look at a neighborhood which is really huge. Okay, that's roughly the idea. So you won't have the neighborhood size increases to have enough points for KNN. Okay, that's the issue with KNN, and that's what's written in this section. Basically, neighborhoods don't make sense in high dimensions. That's the takeaway. Yeah.
So the running problem with this is that it's computationally expensive, or there are also other issues that are
not computationally expensive, statistically expensive, right? In a sense, you need exponentially more data if you want to use KNN. So let's say you are in 10 dimensions. You want to have like 1 million data points to actually, be confident that KNN is doing something right. If you're in 20 dimensions, you need 1 billion data points, roughly. I'm just using figure of speech here. For 30 dimensions, it's not even you probably need a lot more data points to be confident that KNN is doing something correct. Okay. So if you have lots of data, KNN is good enough, end of story. If you have very little data, then you need to make these strong assumptions, like the linear assumption about the expected value of y given x is equal to x. That's what linear regression was making. You need such strong assumptions to do any statistics, okay, any statistical model building. Okay. So that's one of the central points of lecture 2, and the third component of lecture 2 is linear regression, but I'm sure you guys already have seen linear regression several times. It's basically tied to this formula, which is beta hat is, I think I've written it so many times, transpose x inverse x transpose y. So this is a model, but you can also talk about how you got this, and there was some description about how you got this by taking derivative of the residual sum of squares, right, in the vector notation. And there is some classical treatment of linear regression, which means that beta hat, you do this hypothesis testing. You check whether you can have a null hypothesis that the beta j coefficient should be equal to 0. That's a null. From your data, you got a beta hat j to be 0.1 or something, or let's say 10, whatever be the number. Then you can ask whether you can reject the null or not reject the null, which is that beta j should be equal to 0. Okay, this is some classical statistical question that you can ask, and since it's very specific to this linear regression model and is tied to some assumptions, I did not discuss that in the lecture itself, but you can read that section 5.2. Okay. Yeah. So if you're looking at just linear regression, there are two parts. One is how do you compute the linear regression model in closed form, which is this model here. And the second thing is what can you say about beta hat, right? You want to say something about beta hat. That means when I say you want to say something about beta hat, all I mean is some statistical properties, like what could be. Can you test do a hypothesis test that the beta j coefficient should be equal to 0? That would be something that you want to say about your model, right? That's what's written. That's what's captured in that section. Okay. I also introduced bias variance trade-off, but I'm gonna discuss bias variance trade-off again in a few minutes. So I will skip that. So actually, my printouts include things before I sent you the revised versions, which deleted parts. So maybe in lecture 3 I'm still talking about linear regression. Let me just see that. Okay. So in lecture, so is everybody fine with lecture 2? Okay. Actually, yeah, I think so I may be off with topics being in lecture 2 versus lecture 3, so just let me know. Okay. So lecture 3, the main idea was bias variance trade-off. I actually introduced bias variance trade-off again in lecture 5, so let me defer to that because that has the full expression for what is the bias term and what is the variance term. So let me just say so what is the rationale behind like looking at bias variance trade-off now is to kind of understand this choice, the choice of k in KNN, or the choice of subset size, or even the choice of the model. For example, linear regression. So, I mean, these are more specific than the choice of the model. These are also choices in the model, the first two, but they have an additional choice, which is the parameter of the model, like the k or the subset size and so on. So that's the rationale. So we want to understand how does this choice impact let's say EPE, okay, still the expected square prediction error. So we are still thinking of, let's look at just regression and let's look at squared loss. With those two assumptions or those two settings, still we want to understand the choice of different models, right? So that's where bias variance trade-off study comes in. And here we don't really care too much about the training data. Again, we are thinking in terms of the joint distribution between x and y. Okay, just like in the statistical decision theory, we are thinking about just the joint distribution between x and y. How does it impact the bias variance trade-off? The bias and variance are technical terms that you might have seen in other parts of statistics. Here we care about bias and variance of the model itself. Okay, a model like f hat, whatever the f hat is. In the linear case, it's beta hat transpose x, right? And there is a picture. Maybe the revised is better. So bias variance trade-off is all about so on the x-axis is the models. Okay, models have different choices, but for every choice that you make, you can put a model on the x-axis. Okay, and just think of x-axis being model 1, model 2, model 3, model 4 ordered in some way. Okay, it just happens that here we have hidden how it's ordered, but think of the models being ordered in terms of complexity. Okay, how complex the models are. So what makes a model complex? I think somebody was asking earlier, if the models have too much flexibility, like too many parameters, for example, one model has 100 parameters to fit, figure out, and one model has just one parameter to fit, then the one with 100 is more complex. Okay, roughly that's the idea. And bias variance trade-off, at least the output of bias variance trade-off is to understand what happens when you have low complexity models and high complexity models. Okay, with low complexity models, what happens is you will have what is called high bias. Okay, let's try to understand that from the KNN point of view, where we already discussed this KNN K business, right? We said what happens when K is N. Okay, when I choose K to be all my neighbors as in all data in my training data. Okay, yeah. So that would be considered a high bias model. When K is really high, that would be considered a high bias model. Okay, why is that? Because whatever be the pattern in the data, let me give an example here, which is in KNN. Go back to the oranges and blues case. Okay, when K was K was, let's say, I think 15, there was some picture like this. When K was think of K to be, let's say, equal to N. K is equal to N, basically it's saying for any data, any new query point x naught, wherever that is, I'm going to always predict let's say orange. Okay, let's say the number of oranges is 60 and number of blues is equal to 40. Okay, that means that oranges are more than blues. So if K is equal to N, I'm considering all my neighbors, and of course oranges are always greater than blues, so I'm going to predict orange. Now that version, so when K is equal to N, this model, once you fix this, K, that model is a high bias model. Okay, it's not capturing the variation. It's not capturing the variation with respect to the true. Okay, so let me talk about first the true. What is the best model in the classification case? Okay. You remember there was a best model for the regression case, which was the expectation of y given x is equal to x, right? The best model for classification, again, two ingredients. First ingredient is joint probability of x and g. We're talking about classification here, so let's stick with g. Second ingredient is loss. Okay, just take it to be 0-1 loss. Just like in the regression case, the loss is the square loss. Here the loss is 0-1, and the best model for classification is so the g hat at any point x naught is the argmax of the probability of G is equal to K, max over K is equal to 1 to K classes, okay, given X is equal to X. So if you knew this conditional distribution, again, why will we get this conditional distribution? Because we know the joint distribution. If you know the joint distribution, you can compute everything: conditional distributions, marginal distributions, probabilities of any arbitrary events. Okay. If you knew the joint distribution, if choose a 0, 1 loss, this is the best classifier. This is going to say at any given point x naught. Okay. Tell me what is the conditional probability that G is equal to 1. Tell me what's the probability of G is equal to 2. What's the probability of G is equal to 3. You will have all those K numbers. Take the index with the highest number. Okay, that's what this is saying. Okay. In this case, there is only two classes, oranges and blues. So all it's saying is, tell me at this point what is the probability that G is equal to orange and G is equal to blue. Whichever number is highest, it's going to predict that. And that's the best classifier you can get if you knew the joint distribution between X and Y, so X and G. Okay. When you take K is equal to N, so this classifier is called the Bayes classifier. Okay. For some reason. Okay. And it may have some pattern. Okay. It could be, let's say this is the Bayes classifier. Okay. When you choose different Ks, it's trying to, you want to choose a K which kind of reflects the same decision boundary as the Bayes classifier. Okay. So what is the decision boundary? When the probability that G is equal to orange is the same as probability of G is equal to blue. So you are kind of indifferent whether you want to classify that as blue or orange. That's the boundary. Okay. Because on one side of the boundary you will classify it as orange, on the other side of the boundary you will classify it as blue. Okay. Now when you choose K is equal to N, your decision boundary is nowhere close to this one. Okay, in a sense, that actually means you have high bias. Okay, when a decision boundary is not close to the true Bayes decision boundary, it's called the high bias situation. Okay, and when K is equal to 1, let's say, you will have weird decision boundaries. We saw that picture earlier, which had decision boundaries which are like small parts, big parts. Then maybe here this is oranges, here it's blues. Okay, so some regions like this, right? There were some regions when K is equal to 1. This is called the high variance condition. High variance situation. In a sense, here it's going to be low bias. Okay, why is the bias going to be low? Because I chose K to be K equal to 1, it can capture it has the flexibility to capture this Bayes decision boundary. Okay, because I can K is just 1, I'm just looking at local information, very local information to define my decision boundary. It has a lot of flexibility to choose the Bayes decision boundary. Okay, but when I choose K is equal to N, there is really no flexibility. The decision boundary is fixed, and it's in fact at minus infinity and minus infinity, whatever. Okay, think of it in terms of flexibility of decision boundary. I have a lot more flexibility when K is equal to 1. When I have pretty much no flexibility when K is equal to N. Okay. So when I have lots of flexibility, it's called high variance situation or low bias situation. When you have lots of flexibility, and when you have no flexibility, it's called the high bias situation and low variance situation. Okay, low variance because even if you change the data, it's always going to be that the decision boundary is not going to move. Okay, high variance situation because I chose K is equal to 1, suddenly if I change the data a little bit, you will have different decision boundaries. Okay, you can see that. I guess that's in some other lecture. Okay, I will not plot that. Yeah.
So is the best model for classification low bias, high variance?
No, the best model is going to be somewhere in between. Yeah, it's going to be, you want to have both bias and variance low, and that's where that section is talking about. It's trying to decompose your EPE the objective that you care about is the expected square prediction error for regression, and there is an equivalent thing for classification. You care about EPE values or the ERR, the generalization error, and the bias variance section is saying the generalization error can be broken down into two parts: the bias squared term and the variance term. And if you have both these terms low, then the left hand side, which is the EPE, is also going to be low. So you ideally want low bias and low variance. Okay, but depending on the choice of k, I said when k is equal to n, you have very high bias. When k is equal to 1, you have very low bias. So there is some choice of k where you hopefully have low bias and low variance, and that's the right choice of k that you're supposed to pick. Okay, I'm just trying intuition. I'm just connecting across lectures, so maybe this is the first time you're hearing that. But yeah.
So could I say that when k is equal to 1, I'm more closer to the base decision boundary?
No, you're not, right? When k is equal to 1, you're just saying I'll have a constant prediction, whereas constant prediction means the decision boundary, your decision boundary is somewhere like minus infinity or something like that, or infinity. It doesn't matter. There's no decision boundary in the focus, in the region of focus. Yeah.
K equal to 1, we are more flexible, it's more flexible because...
No. Oh, okay, it's more flexible. Sorry.
Because the decision boundary will change with data points.
Yeah, you saw that picture, right? So I think in lecture 2 there was this... was it lecture 2? I'm not sure. Let's see. Yeah, this... it's not here. Okay, it's not in lecture 2. It's actually lecture 1. Yeah, so this one, the moment you change the data, you will have different boundaries, right? That's why it's called high variance. So when k is 1, you will see that these regions, kind of change, right? If you suddenly change the data a little bit by 10%, your whole decision boundary, graphics changes. Okay, that's why it's called high variance situation. But here you have more flexibility because you can capture the decision boundary, the base decision boundary. Okay.
So if we had data somewhere like all oranges on one side and all on the other side,
yeah.
Probably the decision boundary should have been something that is
in between. Yeah.
But in this case in which we had no segregated data.
Yeah.
So could we imagine base decision boundary is somewhere related to when k is equal to 1, or it's
no, base decision boundary, I have plotted it, right? It's in which picture? I think it's in lecture 2. This is the base decision boundary here. Yeah. Even base decision boundary for overlapping data, it can have oranges on the bottom and blues on the top, right? Base decision is the best you can do given the joint distribution between x and y. It can happen with the joint distribution x and y that things can overlap. Think of like two Gaussians, right, in one dimensions. Okay, this is my orange class, this is my blue class. Okay, these are all oranges and these are all my blues. In the sense, so I have this x, okay, x-axis, which is the feature, and if the feature value is, let's say here, feature value is 1, then maybe you classify it as blue. Maybe it's -1 or -1.1, whatever. You classify it as orange. There could be overlap region here, right? Here, let's say maybe it's 0.2 here. It's not clear whether it should be orange or blue, and that's why base decision boundary would still be here, but you may have in your data, blues on this side and oranges on this side. So, okay, but perfectly separated data, base decision boundary will exactly capture things. Okay, this is very orange, blues. Okay. Lecture 1. Oh, I'm in lecture 3. So does lecture 3 also have lasso and subset selection? Subset selection. Okay, in my lecture notes it is in 3. So the next next couple of lectures you need to just focus on 5 methods, right? So there are 3 methods for regression that we looked at. We just looked at linear regression. We looked at variation, which is subset selection. We looked at lasso and ridge. Okay. Linear regression, there was really no choice. We just assumed linear model and we got a model. Okay. Here there is a choice of which coordinates to include in our model, and here again we had a choice of lambdas, which kind of softly trade off what is the weights associated with each coordinate. Okay. So you want to kind of understand why we want to do this. Okay, because if you remember, think of just subset selection. Okay, if I remove some of my input coordinates, okay, then my residual sum of square will always be higher. Okay, that's a important property that you should remember, that if I remove some of my input coordinates, I have less degrees of freedom with my betas. So let's say I had 10-dimensional original input variable was 10-dimensional. Now I reduce it to 2 dimensions. Then the residual sum of squares of a 2-dimensional model is going to be higher than the residual sum of squares of a 10-dimensional model, because I have only 2 numbers to tweak here, beta 1, beta 2 to tweak here. I have beta 1 to beta 10 to tweak there, so I can fit the model higher. Okay, so you can even say that the 2-dimensional model is higher biased, right? It's towards the left side of the model complexity axis. It's higher biased, and therefore it can have lower variance and somehow help you compared to a 10-dimensional model, which will have lower bias but higher variance. Okay. So we want to do subset selection because we want to reduce the variance in our modeling techniques. So, for example, you could have nuisance coordinates which are not at all related to your prediction being there, or you could have collinearity, because of which you get high coefficients, arbitrary high positive and negative coefficients. All this introduces high variance into your model, high variance aspect to your model, and so you want to reduce the variance, and therefore you're biasing by removing some coordinates of your input. Okay, that's what subset selection is doing. So subset selection, lasso and ridge are biasing your models. Okay, they're increasing the bias of your model with the hopes that there's going to be less variance in your model. And so, where is that picture? I think in the 3rd lecture, I think there was this bias variance. Yeah. So think of it this way. So your vanilla linear regression is going to be somewhere on this side. Okay. It may have high test error. So all you care about is minimizing test error, right? So you're hoping that you can subset selection and subset selection, lasso, and linear and ridge regression. All 3 are trying to move towards the left. So you are increasing the bias. Okay. With the hopes that if you are originally on this side with just linear regression, if you move towards the left, hopefully you are having a lower test error in reality. So you are increasing the bias but reducing the variance, and hopefully the combined effect is such that you have lower test error. Okay. So that's the key idea behind doing subset selection, doing lasso, and doing ridge regression. Okay. And lasso and ridge, is just adding a additional penalty term of lambda times beta transpose b for lasso, and lambda times the sum of the absolute values of beta j's for the first one was ridge, the second one was for lasso. Okay, it's just additional terms to the residual sum of squares. Those are 2 additional terms that we added, and there are some properties that we looked at. For example, for ridge, we tried to understand how it kind of does a soft subset selection by reducing or shrinking the coefficients of certain coordinates, right? You may want to look at that section, but it's just to aid your understanding of how ridge regression is performing. Okay, but at the 0th level, you need to understand that ridge regression is to kind of increase the bias of your model and reduce variance. And once you agree with that, then you can think of how it's actually doing it through SVD or PCA perspective. That's what we did in that lecture, right? So I will not have time to actually discuss them. We are already 1 minute over our scheduled time. Let me just take 1 more minute to say that we have also looked at 2 other methods, which is LDA and logistic regression. Okay. These are classification techniques, and what each one is doing, I think I just wrote down the difference between LDA and logistic regression earlier in the class, but they're just trying to kind of capture. If you look at the base classifier, I just wrote down here. Where is the base classifier? Yeah, this base classifier here. Okay, if you knew the true joint distribution between X and G, this is the classifier. I mean, this is the classifier which is defined using this conditional probability, right? Both logistic regression and LDA are just playing with that. So they're just saying probability of G is equal to L given X is equal to X naught, and probability of G is equal to K given X is equal to X naught. They're just approximating. So for example, logistic regression is just approximating this to be beta transpose X. Okay, because you know that these are the quantities that kind of determine your base classifier if you knew the true distribution. Now logistic regression is just assuming this ratio is going to be linear actually. And LDA also does that. LDA assumes with the probability of X given G is equal to whatever L is normal, and that also implies this ratio is linear. Okay. So logistic directly says the ratio of my class given X, class is equal to L given X divided by the probability that class is equal to K given X is linear in X. And LDA is just saying, let me start with the assumption that probability that X is equal to X, probability of X given the class is normal. That will also give me that this ratio is linear. Okay, just happens to be the case. But this is a core assumption for these 2 classification techniques. Okay. And why do we care about this? Just look at the base classifier. We have that same term, and therefore we care about this. Okay, so I guess I'll stop here. If you have questions, just do come see me right after this lecture. Okay. Good luck with the exam.